Alright, so geometric probability. We're going to use lengths and areas to calculate probabilities using geometry. Alright, so all your area formulas are on your cheat sheet, or on your testing sheet right there. You're going to need to use these to calculate the area of certain shapes to calculate the probability of it being in that area. Alright, so we're going to go through each formula step by step to see if we can quickly fill out these examples. Alright, so you figure out what formula you want. So if we're looking at a triangle, you got to find the triangle formula. You're going to write down that formula. Then you're going to write down every variable in the formula and the values that you know. And then you're going to plug it in and chug. That's substitution. And then run the algebra. And then you're going to solve. All right, so here's your area of a square. Area equals the side squared. So here's our square, and our side length is 5. So here's my area formula. And then I identify my variable, because the side is 5, and then I plug it in, and I solve. Squaring 5 gives me 25. So the area of this square is 25. For the area of a rectangle, we use base times height. Now notice, base times height is more accurate because it's the perpendicular distance, it's the height. Okay, for rectangles, we know that they're perpendicular, but I like to use the base times height method because it indicates that it has to be a perpendicular distance. So right here we have find the area of a rectangle with the length of 11 and the width of 6, or the height of 6, however you want to put it. So there's my formula. I identify my variables. L is 6, L is 11, W is 6, or either way, vice versa, however you want to call it. You multiply those together, and you end up with 66 meters squared. Notice it's meters squared. Your units are important. Meters times meters is meters squared. All right. You'll have to find the area of 2 rectangles on the test. They'll be about the same in difficulty. So notice how I said perpendicular distance. The perpendicular distance is important because we use it in triangles and all of our area formulas. And we need to be able to find out what the perpendicular distance is. And it's used in equations like torque, which is force times the perpendicular distance. And we use it in triangles a lot right here. This height that we talk about, this has to be a perpendicular distance. Has to be. This is not the height. This is, because it's perpendicular to the base we're talking about. So I want the perpendicular distance from this vertex to this side length. Alright, so for this triangle here, notice how the 4 applies to the height, this dotted line out here. We have to use the perpendicular distance, which is 4, and then our base is still just this little 5 part here. So first thing we do, we identify our variable, the formula we need. We identify each of our variables. Base is 5, height is 4. We plug those values in, and we chug. If we multiply a half times 4, it's easier than a half times 5. So we just do half of 4 is 2, multiply them together to get 10 meters squared. That's your formula. So for the area of a parallelogram, we have area equals base times height. Again, that concept of height means perpendicular distance, not just the side length, not like a square or a rectangle. We need the perpendicular distance. So using this, we find that the side length is 7. We want to ignore that. That's a distractor trying to draw your attention. No, ignore it. I want the perpendicular distance, which is 6. So my area of a parallelogram is base times height. My base is 12, my height is 6. I plug in those values, I multiply them together, and I get 72 meters squared. Remember, units are important. You're going to have to find the area of a parallelogram on the test, okay? So, for the area of a trapezoid, we've discussed this before, but it's very similar to our mid-segment formula we talked about yesterday. We take the base 1 plus the base 2, cut it in half, and then times it by the height, which is, again, the perpendicular distance, not the side lengths, not any other measurement. All I need is the perpendicular distance between the two bases. So here I see I have some different distractors, I have some different information, okay? It's my job to determine the information I need. This 8 is a distractor. Ignore it. I want the perpendicular distance, which is 7. I want base 1 is 4 and base 2 is 14. So I plug those in, each one of them, to the formula. I got 1/2 times the height, which is 7, times 14 plus 4. That gets me 18 if I add them together. If I take half of 18, I get 9. And then I end up multiplying 7 and 9, and I get 63 meters squared. Okay. So now the area of a circle, or the circumference of a circle, is measured in pi d. Okay. So if I have the diameter, then I just times it by pi. But if I only have the radius, then it becomes 2 times the radius times pi, or 2 pi r. So you're going to need to know, circumference of a circle, 2 pi r, area of a circle, pi r squared. Regardless, you still find the variable that you need to use, or the formula you want to use, and then you just plug in your variables. So we look at a circle. Radius is 9. So if it's got a pi in it, you just leave it in there. Don't try and approximate it with 3.14. Just leave it as pi. And just completely ignore it. The area of a circle is pi r squared. We know that's the formula we need. We identify the variable r is 9 meters. We plug that into our formula. It's called substitute. And when you square it, you end up with 81 pi meters squared. Again, don't try and do 81 times 3.14. Just leave it alone. 81 pi is fine. All right, so now we've already learned that. We learned that in chapter 1. Now we're going to use that information and apply it to the concept of probability. So we're looking for the probability of an event is a measure of the likelihood that the event will occur. That's what it means to be a probability. So a probability of 0 means it will never happen. And a probability of 100% means it will happen, guaranteed 100%. So when you flip a coin, it's a 50-50 chance, right? A 50% chance. That's the probability that it will land heads or tails. So we're going to use geometric probability as a ratio or a percentage that involves the area or length of a geometric figure. As an example, if we talk about statistics, is given the information of what is in your hand, what is in the pail. Probability is given the information of what's in the pail, what is in your hand. So the idea behind statistics and probability is a statistic is something that you've actually pulled out of the pail. And you say, hey, look, I reached my hand in this bucket full of different colored balls, and I pulled this out. This is what was in my hand. Probability is more of a theoretical. If I reached my hand and I pulled out 4 balls out of this bucket, what are the odds that they're all red? Or, what are the odds that they're all blue? Something to that effect. Using statistics is actually trying it, and probability is more of a theoretical, what would happen if I did. So the probability of a segment length. These are really fun problems because they're kind of, the formula is very simple. You just find the length of the whole segment, and then you talk about the length of the segment you want to deal with, and you do a fraction. So if AB is a line segment that contains a smaller segment, CD, and then if a point K is chosen at random across the whole segment, the probability that it's on CD is the ratio of the length of CD to the length of AB. Okay, so visually that would be this. Here is AB, and on AB there's this little teeny segment here, and this is CD. So if I picked a random point somewhere on here, the probability that it's on this segment here is CD, the length of CD, divided by the length of AB. Just like that. Okay. So that's kind of what we're talking about. Let me erase this. All right, so that's kind of the idea behind the geometric probability of line segments. Using this for this example 7.35, we're going to look at the probability that a random point on the line segment AG, that's the entire line segment, okay, is on the segment BD. Okay, so we're looking at this segment here from B to D. Now our formula is the probability is equal to the length of BD over the length of AG. That's their formula for probability. Remember how the bottom part is the whole segment and the top part is just the segment we're looking at? Now, if we plug in our information, we know that the length of AG is 6, and we know that the length of each one, or at least BD, is 2 units. Right? There's 1, 2, 3, 4, 5, 6. The whole thing is 6 units. We don't know exactly how long. And then BD is 2 of those. So I plug in my fraction, and then I reduce my fraction down. Notice how the units cancel. If it's meters divided by meters, those go away. In this case, it's units divided by units. We don't know what they are. We haven't been told meters or feet. Either way, the units cancel. And then we reduce our fraction and we get 1/3. Okay? So, with that, if we do it again, but instead we look at what is the probability of a random point on the line segment AG is on the line segment CF. Now we're going on to the next segment, CF. So CF looks like it's 3 long. So the whole thing's 6, CF is 3. So we say that it's going to be 3 over 6. We know our formula. And then we say 6 and 3, so 3 over 6, cancel the units, and reduce the fraction. Gives us 1/2. So there's a 50-50 chance that that point that we pick at random will be on CF. Okay? This will help you with 11 through 18 on your homework. So the probability using area is the same concept. But before we had a straight line, and we were dealing with how much of that line is we're talking about. But now, if we turn that into an area problem, now let's say I've got a table right here, and I throw a ping pong ball from across the room. What's the probability that it lands in this little cup or this little circular area here? Well, that probability is based on the area of this circle compared to the area of the whole table. Okay, so that's area probability. It's the same. We have, this is the whole area of the table, and this desired area is the area that we're talking about for this specific problem. So if we looked at an arena, like an obstacle course, okay, the whole area of this obstacle course is 20 meters by 30 meters. And now each event takes place in shapes like this. Okay. So if I said, find the area of the rectangular obstacle course, so it's 20 meters by 30 meters. Well, we know the formula for a rectangle is length times width. We know the length is 30 and the width is 20. We plug them in and we multiply and we end up with 600 meters squared. So that's the area of the entire arena, the whole possible area. Okay? Now that formula is right here, desired area over total area. On your cheat sheet, you'll have it on the test. All right, so now, what is the probability that an alpaca will end up on target A? All right, now, we're talking about kind of this theoretical arena for animal shows or something like a zoo. What are the odds that this alpaca will end up on this shape here? Remember, our desired area is the trapezoid. Our possible area is the whole rectangle we just already talked about. That's our probability formula. Now, the 63 meters squared, I tell you that A is 63 meters squared. So I put that on top, and I get 63 meters squared over 600 meters squared. Notice how the meters squareds are going to cross off. We always cancel our units. Units cancel. Now, can I reduce 63 and 60? Or 600, sorry? Yeah, we can reduce 3 out of that. Now I've got 21 and 200. I can't reduce that any further, I don't think. Yeah. So we're left with our probability is there's a 21 in 200 chance that the alpaca will end up on the shape A. Now we can go through this fairly quickly. We look at the bobcat. Okay, what are the odds that the bobcat ends up on target B? So I want to know target B's, the desired result is 72 meters squared. I want him to land on the parallelogram. Okay, that's my desired area. The total area is the whole arena, which is 600 meters squared. Either way, we find the probability formula. We identify our variables, we substitute them in, and then we do some algebra. We just reduce the fraction. The meters cancel off, and 72 and 600 become 3 times 24 over 20. Okay, we can factor out a 4 from that, and we're left with 6 over 50. We can factor out 2's, and we're left with 3 over 25. We have to reduce it as far as we can. So our final answer is 3/25. So we cancel units and reduce. Now this right here, there's a 3 in 25 chance that the bobcat ends up on the B part of the arena. Okay. So if I did this 25 times, probability-wise, it'll happen 3 times out of those 25. All right, so now let's see what's the probability that the crab will end up on target C. All right, so now we have our desired area. What is the area of the target C? It looks like it's the circle hidden behind the crab, but we know from our note packet that it's 81 meters squared. I tell you that target C is 81 meters squared, and you have to plug in the information, cross off your meters. You're left with 81 pi, reduces to be 27 over 20, and we're left with 27 pi over 20. The probability for this circle is going to be 27 pi over 200 times. So if I did this test, this arena with these animals, if I did it 200 times, then the crab would land on part C 27 pi times. All right, so for the dragon, what's the probability that the dragon ends up on target D? The desired area. What is the area of target D? Well, that's 10 meters squared. The possible area is the whole arena of 600 meters. So we plug those in, cross off our units, and reduce. We end up with 1 over 60. So our final answer is 1 over 60. Okay. So, what is the probability that the Egyptian vulture will end up on target E? So I notice up here in the picture it says E is 66 meters squared. That's my desired area. The possible area is the entire arena. So yet again, we use the probability formula, we substitute our target area and our entire area into the formula, and then we reduce out our fraction. Units cancel, we reduce out the 6, and we're left with 11 over 100. So our final answer is 11 over 100. This is a lot of the same concept. I'm trying to get your idea of what's going to be on the test and how you're going to have to handle this. What's the probability that the ferret will land on target F? So target F is 25 meters squared. So that's my desired area. I plug those values in, and I'm left with 25 meters squared over 600 meters squared. Well, again, cancel units. 25 over 600 reduces to be, looks like 1 over 24, if we keep reducing out numbers correctly. So now I'm left with 1 over 24. And that is the probability that the ferret will land on target F. All right, so the killer whales. What's the probability that the killer whale will end up on any of the targets? This is a joke because killer whales don't actually walk, so they can't actually walk into the arena. But there's a 0% chance that killer whales don't walk. We talked about probability. 0 chance means it's not going to happen. 100% chance means it will happen. So for any one of these animals, I could have asked you, what's the probability that it will land in the arena? It's a 100% chance. The animals have to land in the arena because that's the total possible area where they can be. All right, so now let's talk about the probability that an animal will end up on target A, B, C, D, E, or F. Let's say it's going to end up on one of those. We're going to ignore target C, though. So we're not going to do target C. That's my bad. I read that wrong. So we look at the desired area. The desired area is all of those letters, A, B, C, D, or F. Not C, we're skipping C. A, B, D, E, F. So we add up all of those areas. We add them all up. We end up with 263. So now I want to see what that's going to look like when compared to the entire shape. So we take 236 and we divide it by 600 because this is our target area. and this is our total area. So now we reduce our fraction. Units cancel, we reduce the fraction by 4, and then we reduce it again by, no, nothing. We're done. 59 and 150. They can't reduce any further, so the probability that an animal will end up on one of the targets besides C, we're ignoring that one, is 59 out of 150. All right, you will have problems like this on the test, only somewhat easier. All right, so what is the probability that an animal will not end up on target A, B, C, D, or E, and F? Okay, our whole objective here is to say it will not land on the target. Okay, so now when we get a not situation in here, we have to take the total area and we have to subtract the area that we don't want. This is no longer our desired area. This is our unwanted area, if you will. We don't want it to land on there. So if this is the area we don't want it to be, then everything else must be where we want it to be. So when we actually pull this off, we use the probability formula. We have to remove the stuff that we don't want. Okay. So we take the total area and we remove the stuff that we don't want it to land on by subtraction. So when we get that final answer, we get 364. Plug it in and we reduce our fraction. Units cancel, factor and reduce, and I think we're done. We have 91 out of 150. So now, what is the probability that the animal will end up on target D or F? Okay, so the or is important. We'll talk about that again soon. D or F means that I'm looking for the desired area to be either one of those two shapes. So that means we add those two shapes together, 10 and 25, and we end up with 35. So we substitute that in for our target area and the entire area into the formula. We cancel units. We notice 5 goes into both of those. So we reduce out the 5, and we're left with 7 over 120. So the probability that this occurs is 7 over 120. Probability will always be a fraction with the numerator smaller than the denominator. You will never have any other situation that I ask you for. I don't want decimals. I don't want mixed numbers or anything. I want just a fraction, proper fraction. All right, there are only two situations when the probability will be a whole number. So probability is always a fraction, except when it's 0 or 1. Okay, so 0 is a whole number, so that was the probability of 0. It's a whole number. The other one is when it will happen always. Okay, so if it always happens, then it's a probability of 1 or 100%. Okay, those are your two possibilities. Either a fraction is the general way we present probability, but it can also happen where it's a 0 or a 1. All right, please fill out your essential question. What does the probability of 0 mean? What does the probability of 100% mean? We just barely talked about it. You should be able to fill that out on your own. Summarize what you learned in this section and be ready for your homework and your test. Friday is what we just covered today. We have 8.1 Monday, and then we have the test on Tuesday because of the type assembly. So you now know how to do the review worksheets 1 through 10 and the rest of them. We've covered everything in the chapter. All right, don't forget homework due Friday. Saturday, go and get some help from Ms. Kerfman. And there you go. That is 7.5.